Okay, so today we're gonna talk about these, let's say, scary type signatures in Scala, and we're gonna explain a part of them, specifically the ones that have, that are regarding implicit constraints, and we're just gonna go through them bit by bit and understand them. So I'm talking about type signatures like this, which look very involved. They have, this part that might be strange, this part that might be strange. So we're just gonna go through them and start from the simple expressions and then kind of make them more complex. And by the end of it, we'll be understanding what and how this works just fine. So let's start with the simplest thing. And this is, we have a container, which is just a class that holds one value of a generic type A, right? And imagine that you want to add a method to that container, but the method should only work if the container type is an integer. So one way you can do that is you can do that by defining an extension for the container. So you say, here's an implicit extension class for this, and we take the container as a parameter, and we basically fix the type A to be an integer. And we say then, the add method, you just take another integer and you can add these two integers together. And you can do that because the compiler knows that this container is a container of an integer, and therefore the value A here is also an integer, and we can add this. So we can see it in action here. So we create a container, which is a container of integer, and then we can do this either explicitly by instantiating this extension class and then invoking a method on it, or we can do this implicitly because the class is marked as implicit. So if you comment this out, this becomes an error. But if this is marked as implicit and the implicit class is in the scope, you can basically just invoke this extension method on the container itself. And the compiler knows to insert this conversion because it says, oh, you want to invoke this method on a container, but the container does not have this method. Maybe there is an implicit conversion in the scope which will turn container into something that will have this method. And if it finds one, which it does because we have this, then it will invoke the method. Now, if the type does not match, if you try to construct it explicitly, you can see that there's a compiler error here. And it's fairly obvious. There's a type mismatch. We require int, but there's a string. With the implicit resolution, it also fails because the compiler cannot also find a conversion where the types would match, and therefore it cannot find that conversion. Any questions regarding this? No questions. Okay, let's move to the more complicated. So instead of doing this with the implicit class that has an extension, we can achieve the same thing in a bit of a different way. So we can add a method into this container class, and we still have this problem. So you want to add two integers, but from the perspective of this method, you have no idea what type A is. It could be an integer, but it could also be something else. and you need some sort of evidence to witness that the type A is actually an integer. So you can get that evidence by saying we're going to take in an implicit parameter named evidence. It doesn't really matter what the parameter name is. Usually it's named EV, just shorthand for evidence, but we're going to call it evidence, which basically says I need an evidence that A is an integer. And if you're looking at the syntax and you're thinking, well, what kind of syntax is that? So it's nothing special. It's the same thing as here. So you can exchange this and it will work just the same thing. And this is just a type that has two parameters, from and to. And this type is essentially a function that turns A into the integer. And you can write it in this way because Scala has this syntactic thing where if you have a type which takes in two parameters, you can write it in this infix notation. So you can write the type between these. So for example, you can write either int or string. That's one way to do it. But another way to do it would be to write this. So it's just a syntactic sugar. So when we have this evidence, we can basically, take the type A, pass it into the evidence, and then an integer comes out, and then we can do the integer stuff with it. Because this is an implicit parameter, it is eligible for the implicit resolution rules. So you can do it implicitly as well. So you can just type this and the A magically becomes an integer. But there's no magic behind it. The compiler just inserts the call to the implicit evidence function automatically. So now where does these evidence objects, these evidence functions come from? And essentially they come from, in the Scala, there's this object defined, and it has this implicit definition called refl, which is a shorthand for reflexive. And basically it says I can prove that A equals A, which is very obvious, right? But the trick is, basically the trick is this. From inside the container, you don't know what the actual type of A is, right? But from the outside of container, like here, you know what the type is. You know that this is a container of integer. And therefore, you can always say, oh, I can prove that integer is an integer, right? And when you invoke with constraint, here you need evidence that integer is an integer. And you can provide it explicitly like this. You could even provide, a custom function as well. But if you don't do that, the refl function is invoked implicitly, and basically you get this behavior where this method is only invocable only if type A is an integer. So if you have a container of string and you try to invoke this method, there is no type that satisfies this requirement. Because if you try to say, create the refl for string, then it says, okay, string equals string, but that doesn't match the, required type string equals integer, which is not really a type that makes sense. And if you do it, from the other way, then you get a type error on the other side. So the only way you can actually create this value, summon this value, is if, a type equals itself. So do you have questions regarding this?
I have a question about the evidence, and you said that it's actually a type and a function. Can you tell more about how does it work actually?
Okay, so it works like this. We have two type constraints. You can see that it's defined in the Scala library. It's named type constraints. There's two type constraints that we have. This is the weaker type constraint, which says this type extends this type, right? So for example, a dog extends an animal, and this thing extends a function. So you can put a dog into this function, and then you will get out an animal, right? And this is a more rigid constraint, which says this type is exactly, that type. So there's no inheritance involved. So because this thing is a function, right, you can put a value into it and it will come out through the other end. So when you have this, you can say, I'm gonna put 5 into it, and then you get, that integer back. And if you look at the implementation of this REFL, there's a singleton instance defined, and basically you can see there's an apply method and just takes something and just returns it back. Because in the runtime, you do not have to transform the value in any way, but you just need to do this trick in the type system to change the type from one type to the another type. Does that answer your question?
Not really, and I don't know what to ask about it, actually.
Okay, so which is the confusing part? That this is a function?
Yeah, so this is a function, and how, for example, when we pass like int, and when we have a container that contains int value and we pass string, why does the error is producing, and how the compiler knows about it?
Okay, so you're talking about this case, right?
Yes, for example, this case.
So yeah, take a look at the definition of this method, right? It only takes one parameter, right? And then it says, I'm gonna produce a type that says, that both type parameters for that type will be the same A. So
right now, this is a type, not a function.
Well, every function is a type. I mean, every function in Scala in Scala there's this thing called function 1, right? And this is a function, for example, from integer to string. So you get an integer and then you say, let's turn it into a string. And if you look at it, it says, oh, we can change this, definition into this definition. So, but in reality, every function is, if I just assign this, it's an instance of function 1. There's like a trait that has a method here, and it's an instance of this. So this thing that we have here is also a type that extends this type, and this type extends the function one type. Does that make sense?
Yes, that makes sense.
Okay. So with that in mind, what is not clear, like
so for example, as I understood, when we have a container with int and we are passing string to the method, it just check. So we have a function that has two parameters, and one of them is int. Another one is we are passing string, but we are expecting int. I don't know why does this error so when we are passing string to the int container, what's the problem? How compiler knows about it?
Okay, let me kind of come to it from the other side. So why does this work, right? This works because we have this type. First of all, we require the type int equals int, right? And we have this type here, right? And we have this type here because we can invoke this method and it produces this type, right? Now, there's only one definition which provides values of this type, and it's called reflexive. You could, for example,
the sentence.
Okay, so let's try providing this evidence manually, right? Let's say, okay, I need to provide an evidence that a string is an integer, right? Oh wait, this is a sealed class. Yeah, you can't actually provide these because it's a sealed class, so you can't even implement it manually. But even if you try to implement it manually, remember that it should be a function that turns a string into an integer, right? And how do you do that? There's no way to turn a string into an integer safely, right?
You can just return 42, for example.
Well, yes, you could do that, but then it wouldn't be like a proper conversion.
Mm-hmm.
The point is that because the this whole thing is sealed, there's only this one way to obtain values of this type, right? And because there's only one way, the only way you can create an instance of this is if the type is the same type that you expect. So there's no way to create an instance of this type which proves that a string equals an integer. Make sense?
Yeah, that makes sense now.
Okay. So yeah, when you have that, it basically says that I can't find like an implicit value that, you know, proves that a string equals an integer. Whereas in this case, it can find this because it needs, you know, proof that an integer equals integer. So this is the evidence-based kind of extension methods. where you don't provide extension methods from outside of the class, outside of the type, but you provide extension methods in the class, and then you have this evidence which allows you to convert from less specific thing like A into something that you have more knowledge about. So now let's take a look at how those two different things, what kind of difference do they have. And if we have a class hierarchy, like we have an animal and we have a dog, we can have two versions of it. We can have a container that has the constraint version and the container, the extension method for it. And the difference mostly is that, so if we take a look at this, oops. So if we have a container that is invariant, that doesn't have any variance on the generic parameter, the extension method works just fine, because it's, you say, oh, I'm a container of animal, and we can invoke this, and you know, this works great. You can do that. And however, if you try to do that with the some other type, like dog, it starts becoming tricky, because the types do not match anymore. So now if you try to actually, you know, apply this, well, idea doesn't show the error, but it does not compile, because, you know, as far as the type system is concerned, a container of dog is not equal to a container of animal, and therefore it cannot instantiate this, and therefore this extension method does not exist. So one way to override that would be to provide an implicit class for some type A which extends animal, and then it works. So that's one way to override it. But then we also have this. So if we type it like this, then, you know, this stops working, because it cannot prove that dog is exactly animal. But if we have this less strict relationship, then it works, because, you know, a dog extends an animal, and here you say the type A must extend animal. So by having this, essentially you don't need to create extensions like this, and also you can still have totally invariant generic type here, and have variance when invoking these, you know, extension methods with constraints. Do you have any questions here?
So as I understood, for the first question is about the constraint in the, for the evidence constraint. Why, for example, we just didn't add plus to the type A in the container definition, like make it
yeah, that's one way to do it, but sometimes you cannot do that. So if you add plus, then it works. If you define this as covariant, but for example, maybe you want to define this, right? And then you cannot make it you cannot make it anything else than invariant. So there's, in some cases, you're just not able to do that.
And the second question, do I understand correctly that the commented code for the extensions is actually not similar, but equivalent to the constraint approach? So this method, animal containers extensions to this class, and the method extract speech with constraint with the evidence. Are they equal?
Yeah, from the functional perspective, yes. I mean, from the functionality perspective, they work through different means. So probably the biggest downside so far with Scala 2 with extension methods is that they have to be in the scope. And if you want to make them, so this does not allocate anything, because if you take a look at REFL, it has the singleton instance and it just casts it. So there's no allocation, no object allocation. Meanwhile, this allocates a new instance of the class, and you could do extends and eval here to avoid that. But then this thing has to be in some other object, and in our case here it's fine, but in some other cases you then cannot put it in a nice place so it would be automatically discoverable. So this sorry, this kind of gives a better developer experience than extension methods. Are we done with this?
Yes, thank you.
Okay, so now let's go to the final stage, to our extract method, which we looked at the beginning. And sometimes you have, let's say you have a collection or some sort of container, and you don't have, you have this container which also has some sort of context, like let's say option or list or future or something else. And you want to kind of extract that context into the outer layer from the inner layer. So instead of having container of option of something, you want it to become an option of container of something. Sorry. So we can provide a generic function that does that without any knowledge of anything. Well, it has to have some knowledge, but it doesn't have to be specific for the, one extract function for option, one for list, etc., etc. So you can write extract and say, there's gonna be a type, we don't know what the type is, but it's gonna have a one type parameter. So it's a type of the context, something like option, list, future, etc. And there's gonna be another type, which is the type of the value in the context. So for example, integer, string, if you have an option of integer, it would be an integer. And then you use this evidence to say that I know that the type A is actually type f of b. And then you say, I know how to do a map operation on the type f. And I'm going to remind what a functor is. And a functor just says, given an instance of fa, so this, and a function that transforms from a to b, we can turn fa into fb. And we can define different functors. We can define a functor for option. We can define a functor for the list, etc., etc. So when you have this, now you can do this conversion fairly simple. So first you use the evidence to turn the type A into FB. And then you say, okay, I have FB, and I can use the functor to map that FB into the container type of B, of the value AB, right? And this extracts, turns the container of FB into F container of B. And then we can just return that. So it's kinda, when you say it's, you know, in with the voice, it's kinda sounds complicated, but essentially it's just taking the inner layer and wrapping it and turning it into the outer layer using the capability of a functor. And if you would need to do something else, you could also have, like, we have, you know, functors, but we also have monads, and we have applicatives and other type classes that specify the things that you can do with some type. So you could use those capabilities in a method like this. Any questions regarding this?
I'm more questioning about the, so as I understood correctly, I'm looking at the functor. It's very similar to the definition of the previous int isInt function. So if we defined it already somewhere, it will be passed here and it will be used here.
Yeah, so I can show you, like, if we have a container of option of 5, we say extract. Now I'm providing these values explicitly. So, you know, this value comes from here and this value comes from here. So you just provide these values and that's it. But you could do the same thing implicitly. So if you don't provide them, Scala uses the implicit resolution rules to look up these values. And they are the same values that we provided explicitly. And you can see, you know, if this container was of option, this becomes option of container. If this container was of list, this becomes a list of containers. And again, if if the types do not match, like if this is just a string, let's say, you cannot provide the values needed here that would satisfy the types, and therefore if you try to use it, it doesn't work. It just says, you know, no implicit founds for these types.
I have a question about this error, but maybe to some other context. For example, we implemented some class and we want to implement this functor. How can we do this?
So yeah, let's provide a functor for the container, right? So the default place to provide these type class instances is in the companion object. So if we do this and then say, here's an implicit value of functor for the container, right? We can create that, and then we say, okay, so how do we do this? And it's fairly simple. We just create a new container and we pass the a value like this, right? And now you can do, well, this will look funny, but you can actually do a container of 5 extract, and the type Well, it doesn't.
Maybe better option of container.
We do not have extract defined for option. So this extract is defined on the container.
Okay.
In general, it is possible to write like an extract function that would work generically, something like extract that works on like a type like this, and then it turns it into a type like this. But in our case, it's a bit more complicated. In our case, we written extract on this single thing. But if you take a look at the implicits, again, this uses the reflexive method, and this just points into this functor.
Yes, thank you.
So yeah, I think that's it, right? I guess we can try writing something like this, right? Like a generic extract function. So we need this, and we need we need 3 type parameters, and we need to say that's gonna be this. We have a value of this type, and then we say okay, let's extract, and after extraction we're gonna have a GFA, right? Now the question is, what capabilities do we need? And essentially, yeah, I think it needs applicative. I don't have like enough machinery written down here, so there's, I guess I can do like an explanation later down the line with this generic extract. So I guess that's it for now then, right? And bye.